Hello, everyone. Let's continue today with product and quotient spaces. I think Professor Vero have solved. I think he has solved homework 2 for you. So today I would mostly try to focus on quotient spaces. He has started quotient spaces, right? Okay. So, okay, I would review the definition and then we would get to some practicing and some solving some questions about the quotient spaces. So let's just do a review. Let's start with product of two linear subspaces. Sorry. So we can start actually with the set theoretic approach. Suppose A and B are two sets. Okay, still not a vector space or not a field or group or anything. They're just two sets. They just contain some elements. For any two sets like A and B, we can define A cross B, A times B, Cartesian product. So we have A times B. It's a new set. The elements in this set are pairs. So they are of the form A and B, where the first element A is an element of the set A, and the second component B is an element of the set B. Right? That's fairly simple. So for example, if A is a set with only two elements, 1 and 2, and B is another set with three elements, say 4, 7, and 9, then A times B as a set is the pairs like 1 and 4, 1 and 7, 1 and 9, 2 and 4, 2 and 7, and 2 and 9, right? Just as simple as that. The interesting thing is that this concept even makes sense if A and B are not finite sets. They're like infinite sets, like R, right? When we have, if I take A to be R and B to be R, I would get R times R, which is just R squared. Now the point is that if A and B are vector spaces, their product is another vector space. So the interesting thing is that if we have two vector spaces, V1 and V2, if these two are vector spaces, the important thing is that over a field F, they are supposed to be vector space over the same field. I'm not assuming there are vector space over different fields here in this construction. I'm assuming both of them are vector spaces over the same field. So V1 times V2 would be a new vector space over this field F. Okay. And why is it a vector space? Well, what are the elements here? The elements here are of the form small v1 and small v2, where v1 is an element of the vector space v1, and v2 is an element of the vector space v2. In order to say this thing is a vector space, I should say this comes with an addition and a multiplication with the elements in the field, right? So if I take two elements here, if I take V1, so any element here, like U is of the form V1, V2 is a pair. So if I take a second element, U prime would be V1 prime, V2 prime. Now I should say I can add these two. I should say if this new product space wants to be a vector space, I should say I have U plus U prime. I should be able to define this. And the definition is component-wise. So I would add V1 to V1 prime and V2 to V2 prime. There is some small subtlety here, which we should pay attention to. V1 and V2 are not necessarily the same vector space. They're different, right? So V1 has its own addition, and V2 has another addition. They are different vector spaces. So for example, I show one of them with just here. We don't do that usually. I would just show that with V1 and the addition with 1 under it, and then we have another addition for V2. So here, the first component, when I have V1 plus V1 prime, that plus is actually the addition inside V1. The second one is addition actually in another space. So these two additions are they're different. They're in different vector spaces. And the other thing is that if I want to have a vector space, I should have scalar multiplication. So if I have some element in the field, I should be able to define A times U. And again, it is the standard component-wise multiplication. I would multiply V1 by A and V2 by A. Again, there is a small thing here to note, and that's the fact that V1, that scalar multiplication is the scalar multiplication for elements in V1. So that's the scalar multiplication for V1. Maybe here the scalar multiplication in V1 is defined differently with scalar multiplication in V2 if V1 and V2 are different vector spaces. So the first one is kind of scalar multiplication in the vector space V1. The second component is the scalar multiplication in the vector space V2, and they might be different, although we usually don't use these notations and these indices 1 and 2, but it's just good to have them in mind. And by induction, we can define we can define the product of 3 vector spaces. Well, let's just do it directly. How can we define that? Well, the point is that this is the way to define it. We know what is the product of 2 vector spaces. We just defined that, right? We just defined the product of 2 vector spaces. So we understand V1 times V2. So this V1 times V2 now itself is a new vector space. I can think about it as just one vector space, right? So now this would be my number 1 vector space, and I have a second vector space, which is V3. And because I know how to define the product of 2 vector spaces, now here one of them is V1 times V2, and the other one, the second one, is V3, I can define their product. And by induction, we can define the vector space V1 up to times V2 up to Vm for any natural number m, and we would get a vector space. But also we can define them directly component-wise. Here the addition and multiplication, just like product of 2 vector spaces. Here it's just like that. It's component-wise. And we should check they satisfy the properties we expect a vector space to satisfy. Actually, they do, and it's not very hard. So for example, we should say this new vector space V1 times V2 up to Vm has 0 elements. But because what is the 0 element here? 0 for identity, identity for addition, sorry. So we know V1 is a vector space. So V1 has a 0 element. V2 might be a different vector space. It has its own 0 element up to Vm. Now look at this new vector, which you can construct by putting these zeros of these different vector spaces next to each other. You would get an element in the product space. And this is the identity element for addition in this new product space. Same thing holds for inverse. If I take some element here, say U1 up to UM, and I want to say this element in this product space has additive inverse, well, I can do that because U1 is in V1, and U1 in V1 has some additive inverse minus U1. But remember, again, this minus U1 is the additive inverse in V1, right? And for example, U2 in V2 has its own additive inverse. Even these negative signs, somehow these additive inverses, because we have them for each vector space, each of them is vector space, we can do this thing for all of them, and we would get a new vector, minus U1 minus U2 up to minus UM, right? And that would be the inverse of this whole vector U1 up to UM. Okay, so that's the concept of the product of two vector spaces, right? So there are a few things to note here. I'm recording, right? Yeah. So there are a few things to note here. One is the dimension of this new vector space. So I had V1, V2, etc. I looked at their product. I can get a new vector space, and I want to see what is the dimension of this new vector space. What is that? What is the dimension?
Sum from m equal the sum from 1 to m.
That is correct.
Dim m.
That is correct. Yes. So here I'm assuming V1 up to Vm, all of them are finite dimensional. I mean, in some sense, it still makes sense if they're infinite dimensional, but just for simplicity, let's assume they're finite dimensional. How can I prove that? Why is that true? How can I prove this as a theorem? So remember, there are different ways to prove dimension of a vector space is a certain number. One of them was finding a basis for that space, right? How can I use that idea to prove this number is the dimension of this product space?
I guess find a basis for this product space and count the number of vectors in it and prove that it's a base, that it's linearly independent.
That is correct. But here now, suppose I know the dimension of V1, I know the dimension of Vm, I know that, and I want to find the dimension of the product space. How can I use these spaces V1 up to Vm? How can I use them to construct a basis for this product space? That's the idea. So let me explain. So dimension of V1, so I have the vector space V1, okay? If I look at its basis, let's show it with B1. Say B1 is a basis for V1, right? Basis would contain some linearly independent vectors, which they generate V1. Let's use a notation for them. Let's show E1 up to E. What is the index of the last vector? That should be
the dimension of V1.
That is correct, yes, the dimension of V1. So just in order to remember this is for the vector space V1, I put a number 1 here. It's not power. It's just, I just mean these are the basis for the space V1. And then we can look at V2. We have a basis for that. Let's show that with B2. And the basis there would be some other vectors, which they start from E1 and they continue until E dimension of V2. Again, I use number 2 to specify this. These are a basis for V2, okay? And up to Vm, we have the vector space Vm. We can fix a basis for it, Vm, which I show it with E1, M, up to E dimension of Vm. Okay, is this notation confusing? Do you understand? So the index shows the from 1 to dimension of Vi, shows the number of vectors in that basis. And the superscript is not power. It just shows this is a basis for V1, V2, which one, right? Now I want to use these things to construct a basis for this product space. I want to use these to construct a basis for V1 times up to Vm. How can I do that? So suppose I have these vectors. How can I construct a basis for the product space?
Can you do something along the lines of like the first basis vector would be E11, comma 0, comma 0, comma 0, and then E12, comma 0, comma 0, and then you do that for all the V1 basis vectors. And then for V2, you do the same thing, but put them in the second position. So it's 0, E21, 0, 0, 0, etc.
That is correct. That's exactly what we should do. That's correct. So the basis for this product space is like this. So we had a basis for V1. So it was E11, E21 up to E dimension of V1. These vectors, they generate V1. They are not vectors in the product space, right? They are in V1. They are not in the product space. But if I look at these vectors, E11 and then 0, 0, 0, 0 up to Vm, now this is a vector in the product space, right? I have chosen E11 inside V1. I have chosen 0 inside V2 and up to 0 inside Vm, right? Now this is a vector in the product space. Well, completely in a similar way, E12, 0, 0, 0 up to Vm, having 0 there, is a vector in the product space. I can do the same thing like for all of them. Now I have dimension V1 many vectors in the product space. Now look at these vectors, 0, E21, 0, up to 0. 0, E22, 0, and 0, E2, dimension of V2, 0, up to 0. Now, these are again vectors in the product space, and these vectors are a basis for V2. And by just adding 0 on the other components, I get vectors for in the product space. And I can do the same thing for V3, V4, etc., up to Vm. So I would do exactly the same thing for V3, V4, up to Vm. So for Vm, we have 0, 0, up to the last component. I put the basis for Vm. So I would have E1, EM1, EM2, etc., up to EM dimension of Vm. Now, the claim is that these vectors, all of them together, they form a basis for this product space. Okay, so the claim is that this is a basis for the product space. Now, if we believe that, if we accept that claim, then we can count how many vectors we have here. Well, here I have dimension V1 many vectors. Here I have dimension V2 many vectors, and then dimension V3 many vectors, up to here I have dimension Vm many vectors. So the number of all of these vectors is exactly dimension of V1 plus dimension of V2 up to dimension of Vm. Therefore, if this set forms a basis for this product space, the dimension of product space should be the number of these vectors, which is just dimension of V1 plus dimension of V2 up to dimension of Vm. Okay, now, does it make sense? Is there any question up to this point? Is it clear where I'm going? So if there's any confusion, you can just say it now, because it's a good time to reflect on this more. Okay, so I want to say this thing is a basis. I should show two things. I should say they generate the whole product space V1 times V2 times Vm. And I should say these vectors are linearly independent. Okay. Why do they generate all this vector space? Well, any vector there, so I should say any vector in this product space can be written as a linear combination of the vectors appearing in this page. So I should say any vector here, say u1, um. I should say I can write down u1, um, this vector, as a linear combination of these vectors, right? But the point is that u1 to um, this is equal to u1, 0, 0, 0 plus 0, u2, 0, 0 plus 0, 0, u3, 0, 0, 0, and until the last one, which is 0, 0, 0, um. Right? Because, well, why is that? Because we have this component-wise addition, right? Because 1, 4, 5 as an element is equal to 1, 0, 0 plus 0, 4, 0 plus 0, 0, 5, right? When we are adding them, we should add each element, each component to this corresponding component. So I should add 1 to 0 to 0. 1 plus 0 plus 0 is 1. And then I should add 0 to 4 to 0. 0 plus 4 plus 0 is 4. And then I should add 0 to 0 to 5. 0 plus 0 plus 5 is 5, right? So this is the component-wise addition. I would erase this example here. And U1 itself, the important thing about U1 itself is that it's inside V1. So U1 itself can be written as linear combination of the basis of V1. But remember, V1 itself, it can be generated by E11 up to E1 dimension of V1. This set was the basis of V1. So U1 itself can be written as the linear combination of these things. So U1 can be written as, maybe I extend it. So U1 can be written as a number, something in the field. I would show it with E11 times A11 times E1 plus a number, A12, E12. Up to plus a number, A1 dimension of V1, E1 dimension of V1. Okay, so U1 is equal to this thing because U1 is in V1. It can be written as a linear combination of the elements in the basis. And then we have zeros after that, right? We have just zeros plus. I can do the same thing with U2. U2 is an element of V2. V2 can be generated by E21 up to E2 dimension of V2. So U2 can be written as a linear combination of these vectors. I use the scalars A21 for E21 plus A22 E22 plus up to A2 dimension of V2 E2 dimension of V2. And then I have zeros after that. And the same thing holds for all the vectors up to the last one. And the last one is UM. UM is in VM. VM can be generated by its basis. So the last one would be 0, 0, 0 until um. Um is a linear combination of the elements of bases of Vm. So it would be, and the scalar I showed with am1 times em1 up to am dimension of Vm, em dimension of Vm. Now, after writing these things, we can just open and expand all of these things. So this is equal to, so A11 E11 0 0 0 plus A12 E12 0 0 0 plus A1 dimension of V1 E1 dimension of V1 0 0 etc. Now these are just the same vector here. All of them, that sum is just this first vector here. I'm just expanding this vector. I'm kind of opening this sum here, right? And then, so this is just the first vector. And then we have the second vector. These correspond to the first vector in the previous page. Now for the second vector here, we have A21, E21, and then 0, 0. Up to until the last one for the second vector, A2 dimension of V2, E2 dimension of V2, and then 0, 0, 0. This is for the second vector in the previous page. And then we have all other vectors. You should do the same with all other vectors until the last vector. And for the last vector, we have 0, 0. The last component would be AM1, EM1 until 0, 0, 0. AM dimension of VM, EM dimension of VM. Now, and this is for the last vector. And we are almost done because, well, because of the definition of scalar product, we know these are scalars, they come out of the vectors. I can write A11 here in front of this vector rather than being inside. So what I do is I will bring these vectors outside. This is A1, 2. And also this vector here, I would bring it out. So it would be A1 dimension of V1 times 9. And I would do the same with all other vectors. Here A21, it comes out. Here this vector, it comes out A2 dimension of V2 and etc. Here this vector comes out in front of the vector, and in the last one, a m dimension of V. So these things written in red, they are scalars. They are from the field. So our vector, the vector we started with u1 up to um, has written as a linear combination of these vectors, e11, 0, 0, 0, e1, 2, 0, 0, 0, up to e1 dimension v1, 0, 0, 0, and then 0, e2, 1, 0, and etc. up till the last one. And as if you look carefully, you would see these are exactly the vectors we said these are the basis of this product space. And now we have shown any vector in the product space can be written as their linear combination. It means these vectors indeed generate all of this space. So the set of these vectors is a generator for this space. The second thing is we should show they are linearly independent. I would leave that to you as an exercise to think more about it. And after we do that, we are done. We have a set of vectors. They generate this space. They're linearly independent. They have to be the basis of that space. So we have a basis for the product space. Is there any question here? No? Okay. Okay, so up to this point, we mostly talked about vector spaces, vector subspaces. Well, we are kind of going towards understanding the quotient spaces better. One extra step is understanding the affine subspaces. What do I mean by that? So for example, consider R2. It's a two-dimensional space, right? Consider this line which passes through the origin. For example, this is the line specified by this equation, y is equal to x. This red line is a vector subspace. It has the origin, right? It's closed under scalar multiplication and addition. Now we think about this blue line here, specified by y is equal to x plus 1. This is not a vector subspace anymore because it does not have 0. It does not have the identity element in addition. More than that, it's not closed under scalar multiplication. So if I take a vector here in the red space, if I multiply that by 2, I would get this one. So if it's u, it's 2u. As you can see, it's closed under scalar multiplication. If I take a vector in the blue space, u prime, if I multiply that by 2, it would just scale it by 2. So that would be 2u prime. It's not inside this blue space anymore. So although it looks linear and looks flat like a subspace, but it's not a subspace. It's a translation of a subspace. It's a subspace, but we moved it from the center, from the origin. It's parallel to a subspace. So this blue one is not a subspace itself, but it is parallel to a subspace, which is the red one. These objects, they are called affine spaces. So affine spaces, maybe I show the red one with V and the blue one with U. The affine spaces are a subspace like V plus they've translated. So we have moved that. So if you look at this vector here, U prime, if we add this vector U prime to all this space V, it moves V to U. So affine spaces are equal, affine subspaces are equal to vector subspaces plus a vector. We move them, right? So, so these things are called affine subspaces. So the point is that, what about
addition? Question?
Yeah.
Oh, why is it called affine?
That's a good question. The word affine, you mean, right?
Yeah, because I know that's a geometry term, right?
Well, yeah. Yeah, it's a good thing to. Well, let's look at the exact meaning to see if it's what does it mean. Well, based on Google, it has two meanings. The first one is allowing for or preserving parallel relationships, which kind of means what we have here. The second meaning is a relative by marriage, which I'm not sure if it's related to this concept. Yeah, but anyway, I mean, in geometry also parallel transformation is exactly this thing, just moving things around and scaling them. So, and scaling and rotating. So in geometry, it's just like linear algebra. We have linear maps and we have affine maps. And affine maps are the maps which are linear plus a translation. Yeah, yeah, I can think more about the origin of the word. It's a good question. Anyway, affine subspaces are the father and mother-in-law of vector subspaces. Okay, yeah, that's one approach to mathematics. Yeah, that might be true. Okay, let's look at one example. Well, this is a good example here, actually. We have R2, and V here is, if I want to express it as a subspace, I can say V is the elements of the form V and, well, let's say X and X, where X is a real number, which it can be written as the span of this vector 1 and 1. This is, say this is U is the vector 1 and 1. The span of that is the whole line passing through that. And U is that space plus this vector U prime. Well, here we can take, we can take U prime anything. So this is the thing. This is not unique. So I can take this vector U prime to be this one here, or I can take it this one, or I can take it this one. Any vector which starts at the origin and ends up on this affine subspace can be chosen as U prime. So for example, one of them is 0 and 1, this one. So I would erase the others. I take the simplest one. Yeah, it's okay. So okay, so that's how we can present U, and so this is parallel to the vector space V. Now let's look at slightly more complicated example. So for example, let's think about this. We were thinking, if you remember, we were thinking about the vector space of polynomials, of all polynomials over, say, R. So everything of this form, x to the n, so a n x to the n plus a1x plus a naught, where these numbers are real for any n. This is, as we mentioned earlier, this is an infinite dimensional vector space. Any two elements I choose here, I can add them, or I can multiply any vector space by a real number, and they satisfy all the relations we like, right? Now, so let's show this vector space with V. Now, if we take the integral, take one polynomial and sends it to another polynomial, right? So, for example, what is the integral of x squared dx? Well, it's x cubed over 3, but the point is that, as you know, there is a constant c, right? This constant is not fixed, okay? So the concept of kind of affine relation, affine transformation, which I talked about, like adding a number to it, is kind of also appears here. This is kind of like moving something. So if we think about the integral, if we define kind of algebraic point of view to integral, it's kind of can be thought of a affine map on the space of polynomials. So this thing can be thinking about plus r. Maybe I would come back to this example later. Maybe it's a little, I should say a few more things. So I would come back to this one later. So there are a few interesting things. One is that when I have an affine space, we noticed it's not closed under scalar multiplication. Is it closed under addition? If I take two vectors here, is there some here? Let's see. Well, let's just look at this one. I take u here and I take v here. Well, I guess you remember from calculus, one way to compute u plus v is this method. U plus v would be here. And as you can see, it's not really in the affine space. So affine space is not closed under addition. but it's closed under something else. Well, let's say it like that. So here I have this affine space. I can always move an affine space to the origin to get a vector space. So I can always, so I would erase these vectors because we don't need them anymore. We understood that their affine space is not necessarily closed under addition. I can always move a affine space to the origin in a parallel way. So I can move it to get a vector space. So move U to get a vector subspace V, right? So I can do this with a vector U. So if this vector here is U, small u, then U minus U is equal to V, right? Or equivalently, V plus small u is capital U, right? Is that clear? So now the thing using this relation I want to say is that if I take any two elements, say V1 and V2 inside this affine subspace, I can always look at I can subtract them from each other. I can always look at what is V1 minus V2. V1 minus V2 is this vector, this red vector. Remember, if we have two vectors, V1 and V2, V1 minus V2 is a vector connecting them, right? Yes. So here I have V1 minus V2. If you look at this red vector as a vector, this vector really lives inside V. Remember, we can move vectors around. Unlike subspaces, the vectors don't, in this point of view, they don't have fixed initial position. You know, we can move vectors around. So this vector V1 minus V2 is actually in this vector space V. So we can see that here too. So if V1 and V2 are in this affine space U, because any vector in the affine space U minus this vector U is inside V, we understand V1 minus U is in the vector space V, and V2 minus this U is also in the vector space V. Now V is a vector space, so it's closed under addition and scalar multiplication. I can multiply the second vector, this one, by -1. V is a vector subspace, it's closed. So I would get U minus V2 is also in V. I multiply it by -1 as a real number. Let's say we are thinking about real numbers. I just mean it works on any field because it's inverse. Now, this is an element in V. This is an element in V. Their sum should be in V. So we know the addition of two elements in V is an element in V. This should be in V. But what is this? Well, look at this. Minus U plus U. They cancel each other. So we get V1 minus V2, and it should be in V. And this is an important thing. Whenever we have an affine space, we can move it to a vector space. And the point is that for any two elements in our affine space, their difference is in that vector space. So V1 minus V2, if V1 and V2 are in U, V1 minus V2 is always in that parallel vector space. Okay. So that's one thing. The other thing I want to talk about is that we can kind of go the other way. We can start with a vector subspace. So let's say V is a vector subspace here. And we can start to move V around. I can add different vectors to V. I can say, look at V plus U1, I would get this red affine space. I can say, look at V plus U2, I would get this other blue affine subspace. I can say, look at V plus U3, I would get this new affine space. So I can start with a vector space and I can start to move this thing around. I would get a lot of these things, right? I would get a lot of these things. So suppose we have V and we are adding different vectors U to that to get a lot of different subspaces. As I said, sometimes with two different vectors, we get two different affine spaces. For example, here in my drawing, U1 and U2, they give us different affine spaces, but U1 and U1 prime, they give us the same affine subspace. So the point is that U1 and U2, for any U1 and U2, not necessarily the one I have in my drawing, they give us the same affine space if and only if, can you guess? What is the property? What is the condition on these two vectors, U1 and U2, such that if I move V, the subspace V, using these two different vectors, I would end up with the same affine space? What is the condition on these two vectors?
U1 minus U2 belongs to V.
That is exactly correct. U1 minus U2 belongs to V. So as long as we don't have this relation, as long as U1 minus U2 is not in V, U1 and U2, moving V using them, that would give us different subspaces. Okay. Now let's do that. Let's now consider a vector subspace V. Suppose it's a vector subspace, and let's move V with any vector we find. So let's say V is a subspace of another vector space W, and let's move this subspace V with a vector U, and then let's try all different vectors U we have. We would get a lot of subspaces. We get all these parallel subspaces. So this set itself is inside affine subspaces of W. So this set is actually, if for example this is V, this set is all of these parallel translations of V. All these blue affine spaces are inside this space. Consider all of them. Okay, consider all of these blue things. So these blue things, if we think about each of them as one element, this is a kind of important kind of concept in mathematics. Each of these subspaces, they have a lot of elements themselves, right? Each of them has a lot of points. Each blue line has a lot of points on it. It's not just one element, it has a lot of elements. But I can think about each one of them as one element in this space of affine subspaces. Okay. Yeah, that's correct. It's also a partition of W. So I can think about each line here as one element, right? It's kind of like each human, if you think about a human, its body has a lot of cells, for example. I don't know anything about biology, so maybe things I'm saying don't make sense. But anyway, just as an analogy, any person has a lot of cells in its body. So you might think of, if you think about a human as a line has a lot of points on it, has a lot of elements, and each person has a lot of cells. But when we think about society, we think about humans as like the cells of the society, like humans themselves are the building blocks of the society. Here also, I want to think about each line not as a subspace or an affine space. I want to think about each line as just one element here. Okay, so think about each blue line as an element there. So each v plus u, which is one of these. So for example, if I take u to be this one, v plus u would be this guy here. This is an element in this new space. The set of all these v plus u for different u we have, this is called the quotient space. And it's the way to show it is w over v. This is called the quotient space.
Well, isn't the quotient space just W? Or am I missing something?
No, it is not, because it's not. Would you say why you think it is? So I would correct this misunderstanding.
Because U is all the elements belonging to W.
Yes, but you see, a lot of different elements in W would give us the same thing here. You know.
Oh, so it has to be less than W.
Sorry? Say
So,
again.
oh, never mind. Can you keep going?
Yeah, so let me explain one more time. So yes, it is correct. We think about all elements U in W, but that does not mean this set is equal to W. So for example, just to resolve this issue, for example, I'm saying consider elements X in R for every X, and then consider the set X squared. This set is the set of positive or 0, right? The non-negative numbers. Although I'm saying every X in R, the result of this set is not the R itself, is a subset of R. Is that correct?
Yeah.
So yeah, so the fact that one fact is that when I say every X in R doesn't mean, so this thing here also matters, right? That's one thing. The other, why is that true? Why it's not all of the R? Because there are different elements like 2 and -2, which when I look at X squared, both of them go to 4 here. They correspond to 4. So there are 2 elements, but on the right side on this condition, but on the left side, both of them, they correspond to 4, which is 4 here. Now, same thing happens here. Here, I might have 2 different elements in W, but as I said, if their difference is inside V, they correspond to same element there. Just like the case of X squared for 2 and -2, there are different things, their image would be one thing. That also holds here. There are different things in W, which their image on the left-hand side, V plus U1 and V plus U2, they would be the same. And that's why it's not going to be all W. In general, it's not necessarily equal to all W. Okay, if it's still not clear, I can explain it more. So one thing to see, maybe it would help again with answering your question to see if it's not W, is what is the dimension of this space? What is the dimension of this quotient space? The dimension is dimension of W. That is correct, yes, minus dimension of V. Again, if we want to think about these things, these questions, we should try to kind of come up with a basis for this space, okay? So suppose I have this vector space W, I have this subspace V. Say I know the dimension of W is a given number, I know the dimension of V is a given number, and I want to compute the dimension of the quotient space. I want to see what is the dimension of W over V, okay? So the idea is that I should be able to construct a basis for that, okay? So I would do that here. I would do it very fast because we don't have much time. So we have V. We can make a basis for V. Say E1 up to En is a basis for V. I can always extend the basis of a subspace to a basis for the whole space. So let's keep E1 to En. And let's add En plus 1 up to Em to get a subspace for W. Okay, so I want to say I want to find a basis for W over V, and I claim that the basis is this thing. So look at these vectors here, En plus 1 up to En. These vectors themselves are not in the quotient spaces, but if I add them to V, I would get elements in the quotient space, right? So these things are in the quotient space. The definition of quotient space was V plus a vector. And I claim they form a basis for the quotient space. So I should show they generate the space and they are linearly independent. Our times is up, so if you want to leave, you can, but I would continue one more minute to just explain why that's the case. So first, I need to show they generate this space. So let's take any element in this quotient space. As I said, any element there would be V plus some U, where U is a vector in W, where U is a vector in W. Since U is a vector in W, U can be written as a linear combination of these elements, En plus An plus 1, En plus 1 up to Am En. Okay, so V plus U is equal to V plus A1 E1 up to An En plus An plus 1 En plus 1 up to Am En. Now look at this part. Let's call that V, or U prime maybe. We have used that. Look at U prime. U prime is inside V. Why is that? Because E1 up to Em, the way we constructed our basis is that E1 up to En is a basis for V. Therefore, if I only look at this part from E1 up to En, that part, if I call that U prime is an element of the vector space V. And I argue that V plus U prime is equal to V. Why is that true? Well, on the right-hand side, V is the same as V plus 0. That makes it more clear. I said that two of these things are equal if and only if the difference between these two vectors, U prime and here 0, is an element of V. So that's true if and only if U prime minus 0 is an element of V. But U prime minus 0 is just U prime, and we know U prime is an element of V. So the whole thing here in the green box, V plus U prime, is equal to V. So this thing is just V. So, well, what does that tell us? It tells us that what we had is equal to V plus An plus 1 En plus 1 up to Am Em, right? And, well, this is just a little bit notation. Maybe I talk about it more the next time. This thing just can be written. This is just the way we define addition and multiplication on this space. It's equal to An, which I would talk more about next time. An plus 1, V plus En plus 1 up to Am V plus En. Now, these are exactly the things I told you they are the basis. And you can see any element in the quotient space can be written as a linear combination of these. And again, we should show these are linearly independent. Maybe in order to understand the scalar addition, multiplication and addition on this space, you can also think about that yourself to show they are linearly independent. Okay, that's it. Is there any question?
I think I know what was throwing me off. I think it was the fact that like we're moving from having the elements of the vector spaces be vectors. Well, yeah, I mean they're vectors here as well, but having them be, you know, just numbers or coordinates
Well,
that have
they're
maybe
not
lines.
vectors here anymore. Back then they were vectors. Here they are kind of a whole set of vectors as one element.
Of one element in a vector space.
Yeah, that is true. Yeah.
Yeah,
Yeah,
but yeah, I know what you mean.
That's great. Okay, any other question?
I had an unrelated question.
Yeah, sure.
So, actually, I'll wait for everyone else first.
Okay, any other question? Okay, if not, I can pause the recording here, and if you have any other question, we can speak about it after the class. So
Thank you.
bye.